What is an infinite angle? That's what we're going to talk about today. Let's start with something simpler. What is an infinite line? Here I've drawn the Trans-Cartesian coordinate frame. You can see the green diagonal line, and that line runs infinitely long. It runs over all of the real numbers. It doesn't stop. So I've drawn it as green, like in traffic lights, to show that it keeps on going. Now, in transreal arithmetic, there is a greatest number infinity. There's a greatest number minus infinity. I've shown these as red dots, and so a line will stop at plus infinity and minus infinity. And that raises a question for rotation. If you imagine you have a wheel, you mark a point on it and you let it roll forever. That mark keeps going round and round and round and round and round. But when it arrives at infinity, which orientation is the wheel in? Which direction is the mark pointing in? And that's what we're going to answer today. And here is the point at nullity drawn in yellow. Now, when you look at the diagram, you get a good idea of what an infinite line is. Start from bottom left, go red dot, green line, red dot, yellow dot. You can imagine that shape, you can bring it to mind, you can reason about it. You've got a good idea of what an infinitely long line is. But what about an infinite angle? And how do you explain the fact that infinite angles stop at infinity? Well, let's start by drawing a circle. I've drawn a white circle with radius r. I've written the radius in magenta. And I've drawn a straight line above the circle, which is the length of the circumference of the circle, 2 within a pixel. And I've put the length of the circumference on. It's 2 pi r, 2 pi times the radius. If you prefer, it's pi d, pi times the diameter. Here I've marked an arc on the circle. I've marked it on in orange, and I've called it A for arc. In the straight line, I've added an orange line segment, which is A long. Now here, the arc is always less than the circumference. Angles are defined as arc divided by radius. So if we take that orange arc A and divide it by the magenta radius r, then we get the angle theta sub A. Theta sub A means theta subscript A. If I ever wanted a superscript, I would say theta sup A, theta superscript A. But we're working with subscripts, so it's theta sub A. Now, the idea of angle gets generalized to circumference times the number of revolutions plus the arc. And I've written this down as theta sub k equals 2 pi r, that's the circumference of the circle, times k, k is the number of revolutions, divided by the radius to give an angle. So theta k equals 2 pi k. And this generalized notion of an angle, theta includes the number of revolutions, well, the angle of the revolutions, theta k, plus the arc. Which is all very well. We've now got a white line and a bit of an orange line, and we can imagine that going off to infinity, but how does that help? How does that help us understand what an angle of infinity is? For that, we need another model. So here I've drawn a unit cone. The unit cone has height 1 and radius 1. I've marked off the arc in orange. And I'm going to change the length of the horizontal line. The orange part I'm going to multiply by the height. It still represents the angle theta A, but the length of the segment I'm going to multiply by height. And the length of the white segment I'm going to leave the same, but it represents k revolutions. So theta sub k represents k revolutions. And I've got a formula for k. K equals 1 over h minus 1. And we're just about to see why this formula is useful. So let's start off at h equals 1, height equals 1. 1 times theta a equals theta a. I've left the orange line the length it was originally, but k equals 1 over h. H is 1, so k equals 1 over 1 is 1 minus 1 equals 0. I've written down the 0, but the white line has disappeared. So at h equals 1, the angle is just the arc. And that's what we expect. Now, let's look at h equals 2. So the circle we're talking about is halfway down the cone. Again, I've marked on the orange arc on the circle. But the circle is now half the size. It's halfway down the cone. So multiplying the length of the orange line by 1/2 gives us the shorter orange line at the top of the diagram. Theta 1 represents some rotations. Let's work out how many. K equals 1 over h. H equals 1/2. 1 divided by 1/2 equals 2. 2 minus 1 equals 1. So theta 1 is 1 revolution. That white line represents 1 revolution. And we could go on a third, a quarter, a fifth, and so on, approaching infinity. We would be rotating forever and ever and ever without stopping. We would be marking out angles on the green line I showed you at the beginning. But how do we get to infinity, which I showed you as the red dots? Well, we do it like this. When we arrive at the apex of the cone, the apex is a single point. It has height h equals 0. If we multiply the arc by 0, then we get 0 arc, and you can see the orange line has disappeared. Now, k equals 1 over h. H equals 0. 1 over h is infinity minus 1 equals infinity. So I've drawn theta infinity in as a red line. We've arrived at plus infinity. And you can see there's no orange line. This model has correctly calculated that compared to infinity, the finite arc has no effect. So now we have a mental model of where all of the rotations are. An arc starts off at the cone at height 1. Successive rotations occur at height 1/2, 1/3, 1/4, and so on, tending to 0, but not arriving there. That's the rotations along the real number line. When we arrive at the apex, we've got this situation. So, what is this situation? Well, the apex of a cone is a point, and a point has radius and circumference 0. So the angle at the apex is radius divided by circumference equals 0 divided by 0, and that's the number nullity. So now we know that angles minus infinity, infinity, and nullity are all the same. I haven't spoken about negative infinity so far, but positive angles are measured clockwise, negative angles are measured anti-clockwise, and so minus infinity is infinitely many rotations anti-clockwise. Now, infinite and nullity angles, as you've just seen in that diagram of the cone, are consistent with trans-trigonometric diagrams. And trans-trigonometric diagrams contain trigonometric diagrams. So all of the trigonometry you've ever done can be done so that it includes infinite and nullity angles. Infinite and nullity angles are consistent with trans-power series, and trans-power series contain power series. So all of the calculus you've done with trigonometry continues to work. Infinite and nullity angles are consistent with transcomplex numbers, and transcomplex numbers contain complex numbers. So all of the complex analysis you've done before, you can continue to do with infinite and nullity angles. Now, my mate Tiago does Hish and I figured all of this out. If you had figured it out before us, you might have won this Best Paper prize. So, some homework. I'm very pleased that you're watching my YouTube videos, but you can't become a transmathematician just by watching videos. You've got to do some work. So here's some homework. Prove that cos squared x plus sine squared x equals 1 to the power x for all transreal x. And I've put the answers in the examples playlist. Now, if you haven't got any clue how to prove this, look at one or two of the examples. When you get the idea, try some on your own. You don't have to try them all, just convince yourself that you can do it. The examples should appear on the right hand of your screen. If they don't, click on this card. It'll take you to the playlist and you can work your way through the examples. Be totally brilliant, share and subscribe for more.